Okay, in this video I'm going to talk about the Peaceman well connection term and I'm going to explain why XM doesn't use the Peaceman term, and I'm going to give an explanation why we don't use the Peaceman term. But let's start with what Peaceman actually did. What was his claim? Uh, most reservoir simulators do use the Peaceman uh, correction terms, the well connection terms. Uh, what he did was basically set up a grid, like here you can see it in the upper right hand illustration, with one producer, I guess, here, and one injector there in a quarter 5-spot pattern. And he plotted the pressures once he had achieved steady state conditions. He plotted the pressures as a function uh, of the distance from the center of the well block, or from the well. And he plotted that the distance is shown on a logarithmic scale here, logarithmic axis, and the pressure is shown on the vertical, on a linear axis. When doing that, all the pressures, at least the ones in the vicinity of the well, should line up on a straight line. That line, of course, would be logarithmic if you had a linear axis at the bottom. What he found was that the well block itself, the pressure in the well block, actually he took the difference between the grid block pressures minus the well block pressure, and the well block is the grid block that contains the well, so it's 0 here. He's basically subtracted the well block pressure. But it's not on the straight line that you would expect. You can calculate what the average, what the radius would be uh, for the well block. It's about 0.346, I think. And it doesn't fall on the same linear trend as it should. And what he says here in the conclusions of his paper is that in numerical reservoir simulation, the pressure calculated for a well block is the same as the flowing pressure at an equivalent distance r sub 0. For a square grid, that distance is 0.2 times delta x, where delta x is the size of the square grid block, the length and width. And so he suggested to, if you look at this, there's I'm going to show a simple animation here. He straightened out the line and moved that point over to 0.2 to get a perfect logarithmic behavior. And of course, you can extrapolate that point all the way down to the wellbore radius to get the flowing bottom hole pressure, which he states in his second point here in the conclusions. The conventional equation for steady state radial flow then can be used to relate the well block pressure at that radius to the flowing bottom hole pressure at the wellbore radius. So that's basically what he did. He said that the average pressure in a well block is closer to the well than it should be, based on analytical calculations. And that, of course, was pretty upsetting. And if you download this paper from SPE, or 1 Petro, I guess they call it. It comes with an attachment written by a Mr. Mrozovsky. He added a 3 or 4 page attachment to Peaceman's paper where he expressed some concern. And I'm just showing one paragraph here where Mrozovsky says, however, Peaceman has shown that the block pressure is not the average pressure of the block when there is a well in it. And he thinks this is disturbing since a simulator is set up to maintain material balance. If the block pressure is not the average pressure of the material in the block, then a material balance error is incurred. I'm showing this just to illustrate that Peaceman's well term is by no means obvious, and it did cause a lot of commotion in the reservoir engineering community when he first published it. So let's see what's going on here, really. Here I've got an illustration of the fields, of the pressure field, the pressure near a well. And starting at the left hand, up on the right hand corner, this is an attempt to illustrate the pressure in 9 grid blocks. You can see those faint greenish colors, edges of the grid blocks. That's an attempt to show where the grid block interfaces are, and the profile of it is logarithmic in all directions. There's radial symmetry here. And also I have a circle here that shows where the analytical average pressure of the well block. It's illustrating a part of a grid, a 9 by 9, 3 by 3 cells. And this plot shows the pressure along this dashed line through the 1, 2, 3 grid blocks, the well block, the neighboring well block, neighboring grid block, and the next grid block beyond that. Here, the dashed lines shows, this line shows where the average well block pressure is. And that's what you're trying to estimate in your simulator. And here's the average pressure of the neighboring grid block, and there's the average pressure of the block beyond that. These are true analytical averages being calculated by means of integration. And we know that flow between 2 neighboring grid blocks is determined by the gradient of the pressure. That's Darcy's law, basically, between 2 grid blocks. And the simulator uses the average pressures to basically estimate what the pressure gradient is at the interface. And it works pretty well. If you take these two points and draw connect them with a straight line, that would be, or the slope of that line would be the estimated pressure gradient, which an approximation of it, and the accurate calculated one would be the dashed line shown right there at the interface. And you can see there they are pretty parallel, which means that flow between this grid block and that grid block will be very, very accurate, very, very close. A very good match. However, when you look at the influx to the well block from its neighboring block, you see the simulator will estimate it based on the center point of the grid blocks and the average pressures, and that the slope of that pressure line is very different from the actual average pressure gradient at the interface, which means that not enough oil or water, whatever, would flow into the well block. Uh, so since the gradient is vastly underestimated in the simulation, the flow into the well block will be vastly underestimated, and you would get a severe material balance. You would get an accumulation of oil in this block. There are more flowing in uh, from all three sides than is flowing out. And what the simulator does, here I show the same drawing basically. I got the analytical gradient in the dashed red line and the numerical approximation in the in this red line. In order to get the inflow correct, you can see the way the simulator does is to reduce the pressure in the well block until it gets an inflow, a flux across the interface that does honor the material balance. And so when you use the center point of the grid blocks to estimate the pressure gradient and hence the flux between the grid blocks, uh, you do introduce an error. And the only way to correct that is to lower the pressure. And the way, and this is what Peaceman said or showed. If you remember, if this line is actually the straight line on Peaceman's plot is actually the logarithmic line, and the dashed continuation of this line is the dashed one here. He actually moved that point the correct distance to that point. And you can see here how he did it. But of course, he didn't correct the pressure in the well block. It's still far too low. And in fact, it could be, depending on the fluid, you could have uh, the, drop the pressure below the saturation pressure, and for example, gas can come out of solution unintendedly, or you know that shouldn't come out of solution. And or if you are undersaturated, the pressure can drop, and as a consequence, the viscosity of oil drops more than it should. So both the saturations and the viscosities in this well block would be wrong as a consequence of the calculation of this slope of the two pressure points here in the well block and the neighboring grid block. So XM, we are not happy with simply moving this point down there when we know it should have been up there instead of going to 0.2 as Peaceman suggested. We want to make sure that the inflow is correct and that the pressure is back to where it should be, because we don't want gas coming out of solution or the oil viscosity to drop to an erroneous value. So here's here's the calculation. I'm not going to spend too much time on this. If you want to look at the equations, you can stop the video and I guess zoom in and get it all there. But what I'm showing here is, uh, and I'm using square grid blocks. Both sides are delta x, just for the record. And I've calculated uh, the average pressure in the well block. It is shown here, and these equations show the average pressure in the neighboring block here. And I also have calculated the average pressure gradient exactly at the interface. That is shown here. So since I have the average pressure there and the average pressure there, I can calculate the approximate gradient that a simulator would do if if the pressures were correct. And that's shown here. This is the approximate gradient. That is the accurate, the analytically calculated average. And you can see that the ratio, the accurate ratio, the accurate gradient divided by the approximate gradient is a constant of 1.47. So that the true influx is 1.47 times higher than what you do get from the numerical approximation. So you can make sure you get the right influx by shortening the delta x here when you estimate the, the inflow or the flow from this block to the next, or you can, which is equivalent to shortening the distance, you can multiply the transmissibility by 1.47. And that's what XIM does. XIM internally, behind the scenes, you don't see it, behind the curtains, so to speak, XIM multiplies the transmissibilities into a grid block with an active well with 1.47 if it's a square grid block. If it's a rectangular grid block, there are uh, other values. But just to summarize, XM assumes that the equivalent well block radius is 0.346, not 0.2 as Peaceman does. So we move the pressure back to where it should be, and we make sure that the inflow is correct by multiplying the transmissibility by 1.47 so that the well block doesn't get choked, and to maintain material balance. So what about rectangular grid blocks? Here I got illustrating where one length is A and the other is B, and I'm going to show the transmissibility multiplier for the B side. And C here is defined as B divided by A. And here's the formula for the transmissibility multiplier for the B side, given this definition of C. If you want to get the transmissibility multipliers of the A side, you just invert C and put it back in this equation, and you get another value. And also you use the correct wellbore radius in a rectangular grid block, which is specified here. This radius, of course, is, or as you could expect, is symmetrical in A and B, because there's only one radius. Here's the same thing, depending on the different C or the different B divided by A ratios. I've got the transmissibility listed here at different values of C. Across the B side, the in this case the dark blue side, and across the A side, which is the pinkish side. And when you plot the values, you can see that they all, or you can read them from the plot if you don't want to actually go to the equation and calculate it. What you see here is that when A equals B, in which case C would be 1, we're back to the standard 1.47 that we have from a square grid block. And that's pretty much what I wanted to say. That this is how XIM does it. We use transmissibility multipliers to ensure that the well block pressure is correctly, and to ensure that the well block viscosities are correct, and to ensure that the well block saturations are correct, and to ensure that the bottom hole pressure in the well is correct. So we may follow up. We have plans of following up this this blog with another blog showing how to model a fractured well, but that will be later on. For now, I'll just say thanks for watching, and I'll see you again next time.